Hello everyone and welcome to a class on the digital signal processing. We will continue with our discussion on the discrete Fourier transform. If you recall, in the previous section we have discussed about how it is possible to reconstruct a time domain signal using the samples that are obtained from the frequency domain representation of this signal. The discrete Fourier transform is represented for a signal like this. Suppose if x of n is the discrete time aperiodic signal, then the discrete Fourier transform, that is DFT in short we can write, of this x of n is represented as x of k. What is x of k? The formula is like this. It is given as summation of x of n e raised to minus j 2 pi by n kn. Okay, here the n ranges from 0 to n minus 1. So you can remember this expression over here. As you can see, there are 3 variables here. One is this small case n. The range of n is from 0 to n minus 1. There is a value of k also over here. So this k is 0 again to n minus 1. And this capital N happens to be the number of points that are taken from the Fourier domain representation. So if you remember our previous class, this x of j omega, if magnitude, suppose it is like this, it's a periodic representation, it is periodic. So we had taken samples of this over one cycle, say from 0 to we had taken n samples over the range 0 to 2 pi. So this is the frequency. So over the range of 0 to 2 pi we have taken several samples. So each of this sample is represented as k equal to 0, k equal to 1, k equal to 2, k equal to 3 and so on. So up to n minus 1. So the k over here represents the index value of that sample. This is the formula for, you can say, transforming a time domain signal x of n into frequency domain representation x of 2 pi by n k, or in short we can write it as x of k. So this is the expression for transforming. The n happens to be greater than or equal to L. So here the L is the length of x of n. So previous videos you can refer to for more discussion on this. And since we are obtaining the frequency domain samples at each of the k and obtaining the and evaluating, you can say evaluating x of omega, we call this transform as discrete Fourier transform. And on the same lines we can also obtain the inverse of the discrete Fourier transform, that is, given x of k, how do you obtain x of n? So x of k to x of n should happen through IDFT, that is inverse discrete Fourier transform. So the formula for the inverse discrete Fourier transform is 1 by n summation x of k e raised to j 2 pi by n kn. Here k is 0 to n minus 1 and n happens to be 0 to n minus 1 as well. So we have both equations here. One is equation number 1 for Fourier transform and equation number 2 for inverse Fourier transform. I insist that the students understand each and every part of this expression thoroughly, so that applications and understanding of these concepts is more easy. The Fourier transform that we are looking at, both of these are periodic in nature. That is IDFT as well as DFT. Both of them are periodic. So, periodic. So, what does that mean? That means x of k is same as x of k plus n with a period of n. So, this can be very well proved if you were to take the Fourier transform. So, the definition of Fourier transform is given in equation 1. What if x of k is this x of n e raised to j 2 pi by n k n, then what would be x of k plus n? Therefore, x of k plus n can be written as summation x of n, no change in this. N is ranging from 0 to capital N minus 1, again no change in that. And this e raised to minus j 2 pi by n, no change in this either. But the k value that we see over here, that is to be replaced by k plus n into small case n. Now let's see what happens further. So x of n e raised to minus j 2 pi by n k n into e raised to minus j 2 pi by n capital N into n. Now, if you observe this second term over here in this range, this is numerator n and denominator also we have n, so that can be cancelled. So, the remaining term happens to be e raised to, only this term happens to be e raised to minus j 2 pi into n, and this is nothing but cos of n 2 pi minus j sin n 2 pi. So, this whole thing is equal to 1. You know, n and each of the case, what is the range of n? N happens to be varying from 0 to n minus 1, only integer values are there. So, integer multiple of 2 pi happens to be 2 pi again. So, for example, if n is 0, then 0 into 2 pi is 0. If n is 1, then it is 2 pi. If n is 2, it is 4 pi. If n is 3, it is 6 pi, 8 pi, and so on. So, cos of 0, cos of 2 pi, 4 pi, and other thing happens to be 1. And the sine of the same term will be 0. So, this whole thing is equal to 1. So, this entire thing can be replaced by 1. Now, the remaining terms that you are seeing over here, where the range of summation is n minus 1. So, this remaining term over here is nothing but x of k as per our equation number 1. So, we could prove that the Fourier transform, discrete Fourier transform is a periodic transform. So, x of n, x of k is equal to x of k plus n. This same I urge the students to try out the same for IDFT. Is IDFT periodic? And there also we can see that the IDFT is periodic there. Now, for the convenience, what we will do? See, you are been writing the definition of the Fourier transform, discrete Fourier transform as per equation number 1. So, in equation number 1, the term that you are seeing over here, that is e raised to minus j 2 pi by n k n. So, this term is e raised to minus j 2 pi by n k n. So, this term can be more conveniently written as w n raised to k n. Okay. So, the name given to this is Twiddle factor. The name given is Twiddle factor. So, this term, that is e raised to minus j, this is only for convenience. So, we write it as w n raised to k n. and with the incorporation of this, the DFT formula will now become x of k equal to summation as from the equation 1. So we are looking at the equation 1. So from equation 1 it will be summation x of n, n is 0 to n minus 1, w n raised to k n. So this is our discrete Fourier transform. And on the same lines, the inverse discrete Fourier transform is written as x of n equal to 1 by n. So summation x of k, you can observe here, this is w n raised to minus k n. N is k is equal to 0 to n minus 1. So this is our expression for the inverse discrete Fourier transform, IDFT. So the students can use these two expressions to determine the Fourier transform, discrete Fourier transform and IDFT. Here the range of k is 0 to n minus 1. In the other equation, that is IDFT equation, n is ranging from 0 to n minus 1. Now let us use this expression to determine the discrete Fourier transform of some expression, some signals. Let us consider the first signal. Compute the 4-point discrete Fourier transform of x of n equal to, let us consider a signal like 1, 2, 1, 3. This is the signal. So this signal we need to find, or we need to compute the DFT. Now I draw your attention to this thing over here, that is 4-point. When you actually take the Fourier transform of this signal, just let us assume that the Fourier transform is a periodic representation like this. It will be periodic, that is x of j omega will be periodic. So let me write even the magnitude. Now I am going to consider only one cycle of this continuous representation of x of j omega. From this we will take only 4 samples, 1, 2, 3, 4. So at k equal to 0, k equal to 1, k equal to 2 and k equal to 3. So reason is we have been asked to determine 4-point DFT. Suppose if we were asked to find say 8-point DFT, then apart from this, I would have taken one sample here, one sample here, one more here and one more here. So that would have made it totally 8 samples. So the idea is, it depends on how many samples we are expected to take from the continuous representation. Continuous representation obviously has infinite number of points, and it is very computationally as well as representation wise in a digital system it becomes impossible. So we will have to obviously take some number of samples from it. So as per the question, it is 4 number of samples. Now it means n is equal to 4. And what is the formula for the DFT? It is x of k from equation 1 just now that we have written. It is summation x of n w n raised to k n, n is equal to 0 to n minus 1. This is the formula for the DFT. Over here it is summation x of n. In place of wn we will write w4, w4 raised to kn, n is equal to 0 to n minus 1. N happens to be 4, 4 minus 1 is 3. So this is the expression. So this is the expression for x of k. Now let us expand this expression, that is x of k equal to, for n equal to 0 what is the value, for n is equal to 1, n is equal to 2, n is equal to 3 and 4. Let's see. So x of 0 w4 raised to k into 0 plus x of 1 w4 raised to k into 1 plus x of 1 w4 raised to k into 2 plus x of 3 w4 raised to k into 3. This is the expression. Now the same we already know the values of x of 0, x of 1, x of 2 and x of 3. Let us substitute that. That is x of k is equal to x of 0. What is x of 0? As per the given expression, the first value is 1. 1 into w4 raised to k into 0. No matter what is the value of k, it is k multiplied by 0. Therefore, this becomes 0 plus x of 1. X of 1 is 2. w4 raised to k into 1 is k plus x of 1 happens to be 1 again. 1 into w4 raised to 2k plus x of 3 is 3 w4 raised to 3k, right? So this 1 over here and 1 over here is obviously can be replaced. So x of k equal to 1 into w4 raised to 0 is w4 raised to 0 plus 2 into w4 raised to k plus 1 into this can be written as w4 raised to 2k plus 3 into w4 raised to 3k, right? So if you look at the representation in the general form of DFT and specifically for n is equal to 4 point, that has been expanded as shown in the last expression over here. Now the last expression that is being put in this green box over here is a function of k. What is the range of k? We already know that k is ranging from 0 to n minus 1, and in this case n is 4, therefore it is 0 to 3. Therefore, this is a general equation for k. Different values of k can be substituted and we can obtain the individual values. So, for k equal to 0, let us see what is the value of k equal to 0. That is x of 0 is w4 raised to 0. Reason is this term remains as it is because there is no k term over here. Whether k is 0 or 1 or 2, any other value, it doesn't matter. The other value, that is 2 into w4 raised to k. So this happens to be w4 raised to, now k is 0, so this is w4 raised to 0. On the same line, I will write w4 raised to 2 into 0, which is 0, plus 3 into w4 raised to 3 into 0. This is also again 0. Now it all finally is independent of all the variables. Previously we had written that wn raised to kn is e raised to minus j 2 pi by n into kn, right? Therefore, on the same line, what will be w4 raised to 0? w4 raised to 0 is e raised to minus j 2 pi by n, that is 4 in this case, into kn. Kn, in place of kn we have 0, so this is 0. So we can write it as e raised to minus j into 2 pi by 4 into 0 is nothing but 0. So we can write it as cos of 0 minus j sine 0. Cos of 0 is 1, sine 0 is 0. So this whole value is 1. Now the quick calculation of the Twiddle factors is essential. Therefore, if you see here, the x of 0 that we are trying to determine, it is w4 raised to 0 plus 2 times w4 raised to 0 plus w4 raised to 0 plus 3 times w4 raised to 0. Each of this w4 raised to 0 value is nothing but 1. So I can confidently write that this is w4 raised to 0 is 1, 2 into 1 plus 1 plus 3 into 1. So this is 1 plus 2 plus 1 plus 3. So this is whole thing equal to 7. So x of 0 is 7. So 3. So x of 0 is 7. What does it mean? So let us again go back to this representation over here. So this is the kth value over here. So the value of the signal over here happens to be 7. Okay. So we are now taking samples from the continuous representation as shown in this representation. The waveform that I have drawn is just a hypothetical waveform, assuming that it's a periodic signal. It could be in a different way also. The given signal is 1, 2, 1, 3, and we are trying to determine the discrete Fourier transform, and we are taking 4 points. So the first point that I have shown here happens to be x of 0, that is 7. Now let us see what will be the second sample. Where is the second sample? For k equal to 1, this is the second sample. So I shall write for k is equal to 1. The expression becomes, I will take the values from this boxed diagram equation. So x of 1 means x of k is equal to w4 raised to 0. You can see it is not having any k term. So whether k is 1, 2, 3 or any other value, it remains w4 raised to 0 plus 2 into w4 raised to 1, because k is 1, plus w4 raised to 2 into k. 2 into 1 is 2, plus 3 into w4 raised to 3 into k. 3 into k is 3 into 1, which is 3. Just like the previous example, sample at k equal to 0, we calculated w4 raised to 0 and other values. Each of the twiddle factor was same. But when k is equal to 1, you can see the first term is w4 raised to 0, second term is w4 raised to 1, third term over here is w4 raised to 2 and w4 raised to 3 also. So individually we need to know what these values are. As far as w4 raised to 0 is concerned, we have already determined this value. On the same line, let us try to find out what is w4 raised to 1. That is e raised to minus j 2 pi by 4 into 1, which is nothing but e raised to minus j pi by 2. Okay, so this can be written as cos pi by 2 minus j sin pi by 2, and we know cos pi by 2 is 0, 0 minus j sin pi by 2 is 1. So this whole thing is minus j. So w4 raised to 1 is minus j. On the same line, let us find out w4 raised to 2. w4 raised to 2 is e raised to minus j 2 pi by 4 into 2. That is e raised to 4 pi by 4. 4 and 4 get cancelled in the denominator. So it is e raised to minus j pi. E raised to minus j pi is cos pi minus j sin pi. This happens to be minus 1. So you can write that expression, fill in the values, and then you can find the equivalent value, that is w4 raised to 2. And on the same lines, when we evaluate w4 raised to 3, the value that you will get is plus j. Okay, so we have determined w4 raised to 0, w4 raised to 1, w4 raised to 2, and w4 raised to 3. So these are the 4 values that we are interested in. So I will use the same here. w4 raised to 0, as already shown, it is 1, plus 2 into w4 raised to 1 was shown to be minus j, plus w4 raised to 2. w4 raised to 2 is minus 1. This is minus 1, plus 3 into w4 raised to 3. w4 raised to 3 is j. So you can see here there is plus 1 and minus 1 can be removed, and we get plus 3j minus 2j, which is just j. So x of 1 is j. This is the value. Let us continue this calculation. Now for k is equal to 2. When k is equal to 2, from our boxed expression over here, we get x of 2 equal to, in this expression I will substitute x of 2, that is w4 is to 0 plus 2 into w4 is to 2. W4 is 2, this value is also known to us. Then w4 is to 2 into 2, that is 4, plus 3 into w4 is to 2 into 3, that is 6. So we know the values of w4 is to 0 and w4 is to 2. We have calculated this, but we still don't know what is w4 is to 4. Let us substitute w4 is to 4, and let's see what we get. E raised to minus j 2 pi by 4 into 4. So this 4 and this 4 get cancelled. So we get e raised to minus j 2 pi. Now here we had derived the e value of e raised to minus j 2 pi. So we can write it as cos 2 pi minus j sin 2 pi. So this value is again 1. You can write 1 minus j 0, but still it is 1, like this. So this is the value. So we got to know this value, and finally we need w4 raised to 6 also. Let me find out that value first. So w4 raised to 6 is nothing but e raised to minus j 2 pi by 4 into 6. We can write it as e raised to minus j 12 pi by 4. 12 pi by 4, or e raised to minus j 3 pi. So this value is cos of 3 pi minus j sin 3 pi. Cos of 3 pi minus this value happens to be minus 1 minus j 0, which is minus 1. Okay, so we got the value. So the w4 raised to 6 can be calculated as determined as minus 1. So when I substitute all these values in this expression, I get w4 raised to 0 is 1 plus 2 into w4 raised to 2. We have determined it to be minus 1 plus w4 raised to 4. We determined it as plus 1 plus 3 into w4 raised to 6. W4 raised to 6, we determined the value to be minus 1. So when I substitute this minus 1 over here, I get 1 minus 2 plus 1 minus 3. So this value is equal to minus 3. So x of 2 value is minus 3. Okay, this process needs to be continued for all the values of k. What is the range of k? K is from 0 to n minus 1. In this example, n is 4. I am reiterating that. So since n is 4, n minus 1 happens to be 3. So 0 to 3. In this case, we determined k equal to 0, k is equal to 1 has been determined, k equal to 2 has been determined. Last remaining value is k equal to 3. Let us find out what would be the value of x of k at k equal to 3. So at at k equal to 3, we get x of 3. X of 3 is equal to W4. I am going to refer to the boxed expression over here. In this expression, I will substitute k equal to 3. This becomes independent of k. This is anyways independent of k. This is k equal to 3. When this is 3, it becomes 2 into 3, that is 6. And this is 3. This is turning up to be 9. So 3 into 3. So I shall write that expression as W4 raised to 0 plus W4 raised to 3 into 2 plus W4 raised to 2 into 3, that is 6, plus 3 into W4 raised to 3 into 3, that is 9.